All right, so this first one is kind of to ease us into a more difficult problem. So we're going to follow those 4 steps and kind of work our way down and then solve the problem. So we're supposed to first, again, identify the output variable to be optimized and the input variable or variables. Then we're supposed to sketch and label the diagram. Then write a model for the output variable in terms of one input variable. And then finally answer the question posed. So we have a garden area, and a rectangular shaped garden has one side along the side of a house. The other 3 sides are to be enclosed with 60 feet of fencing. What is the largest possible area of such a garden? All right. So first, A, identify the output variable. So let's see here. Let's call it optimization. And so this is going to be our output. And what do we want? We want the largest possible area. So that's going to be our output is the area. We want to optimize that. We want to maximize. Now what's the input? All right, well, we're going to have a rectangle. So we're going to have, an X and a Y, some kind of a side. So maybe we can call this the short sides and this one the long side. Doesn't matter. You can use width and length. You can use whatever you want. I'm just using X and Y. Now, so for part B, we need to sketch the thing. Well, this is kind of like the one I said before. We have this house and we have this rectangular garden we're going to have outside here. So instead of a patio, we're going to have a garden. And I said the short sides were X. And again, it doesn't matter how you're going to do it as far as you draw the short sides are X and the long side is going to be Y. Now, what we need to do is part C is start setting up our equations. Now, this might take the next page even, so I'm just going to, kind of go from here to here, and now I'm going to go to here. Well, what do we know? Well, we know 60 feet of fencing has to go around. So if we add that plus that, all of those equal 60. So if I take x plus y plus x, and that's supposed to equal 60. So what does that give me? Well, that's 2x plus y equals 60. Now, I'm going to solve this for the easiest possible one because remember, we have to do this in terms of one variable. So I'm going to solve this for y, and if I take 2x to the other side, that's going to be 60 minus 2x. Okay, so that's one equation. That's the perimeter. Now, I want to maximize the area, right? So that's going to be my other equation. Area is equal to, well, what's the area of this? Well, it's just be x times y. Now, what do I know? Well, I know y is equal to that. So x times 60 minus 2x. And so then I multiply that, and I'll have 60x minus 2x squared. And so that's going to be my area. Now, when I do this, I should probably write that as a function of x. So I'll say a of x is equal to 60x minus 2x squared. Now, when I'm doing problems like this, what's going to end up happening? I'm going to get a graph of this. Now, with the minus the 2x squared, well, what's that going to be? I'm going to maximize, so it's going to be a parabola. It's going to look something like that. So I'm going to have some max peak up here, and that's going to be what I get. Now, if I'm going to do that, I also need to know what the derivative is and where the derivative hits 0. And when it hits 0, it's going to line up exactly with that max. And so what I need to do is I need to take the derivative of this. Taking the derivative of that, I get 60. Then I have minus 4x. Now, there's 2 or 3 ways we can do all this because we're going to have different things. We can go ahead and we can plot this and then plot the derivative, find it all on the graph, and that might be the most common way. So if you keep doing it the same way every time, that might be best, because what if we had instead here a cubic or maybe a quartic? Then our derivative will be either a quadratic or a cubic, and trying to get that equal to 0 by hand is going to be a little harder. But what if we go in here and say, okay, well, our graph originally was going to be 60x minus 2x squared. Now, I've said also plot this. And so what I should probably do is make sure my window is going to be large. I'm going to only want positive x values. Maybe let's go for x. Let's do, I don't know, 45 for a max. Let's go by fives. Now, I don't know. We can always have a negative here because our derivative could go negative. So let's keep that. Let's go up to, I don't know, again, I don't know, 45, and let's go by fives. All right, so it looks like we probably should get a lot higher, but look here. We knew we were going to get a line because it was the equation was area, the derivative of it was minus 4x plus 60 or 60 minus 4x. So we have a slope intercept form. And so we know that we could get that easily and find what the x was. But let's go ahead and increase our window to the top. And so maybe, I don't know, let's go to 250 and let's change that to 50. I don't know if that's even going to be high enough. Nope, it's not even high enough. So again, it really doesn't matter. Let's go up to 500. There we go. and so that peak corresponds to where that crosses the zero. So what we're going to look for is the zero, which is number 2. And we want it on the red one. So we can come back up here. Now we're on the positive side here. That's going to be our left bound. That's our negative side. And if you really saw that when we went back here, it already gave us the value here. So, but we can hit enter and it tells us, yep, you're right. The zero is at x equals 15. Okay. So let's plug that in here. So what we did was we said, well, a prime, or the derivative of a, is we need to set that equal to 0. And when we do that, x was equal to 15. Okay, or we set this equal to 0 and we solve for x and we get 15 as well. So either way we do it, either by just by hand, we could say, 60 minus 4x equals 0, 60 equals for x, divide by 4, and x equals 15. Or we saw that, when we went to the graph, here at 15 was where it crossed and gave us a 0. But that's our x. Well, guess what? We can now find y. Y is equal to 60 minus 2 times 15. Well, 60 times 2 minus 15 is going to be 60 minus 30, which is 30. Okay. So, what does that say? Now let's make sure we have all of it. What is the largest possible area of such a garden? So it looks like if we go back over here and go ahead and draw our picture in, our x was 15, and that's feet, and our y was 30 feet. And so our area is going to be 15 times 30, which is going to be 450 feet squared. So that's going to be the area of our garden, okay? And so, that gave us, our length and widths and our area. But this is really what they were looking for. And so that's the answer to the question posed. What is the largest possible area of such a garden? 450 square feet. Now, our model for the output, if we circle that, what was the model? Well, this was our model we used. Okay. And our diagram, well, that was our diagram. And here's our input and output optimization. Okay. So those are the items that you're going to be needing to solve any of these problems. Now, some of them, like I said, you might not actually have to draw a picture because it's not going to be a geometric. It's going to be only equations. It's never going to have a picture of it. But a lot of them, you will be drawing some sort of picture. All right, so let's stop there and I'll come back with another one.